I am a graduate from the Faculty of Robotics in AGH University of Krakow. And for my master thesis, which was supervised by Dr. Paweł Zagórski, I worked on system identifying the craters on the lunar surface. So in recent years, we can observe the rapid increase of space missions focused on Moon itself. As you can see, the interest in exploring the Moon is growing, especially now. If you look at the plot, you can see that the manned missions number is also growing in the future. Of course, those are mostly plans, not confirmed missions, but the interest is growing. So just to remind you about some most important examples in recent years, in the last 2 years, we have seen not only the flight of Artemis 1, but also landing of Indian Chandrayaan-2. The capstone satellite was the start of Lunar Gateway project, and Luna 25 crashed into the surface of the Moon. And we hope that in coming years will bring to us, most importantly, the manned Artemis missions. Maybe the assembling of Lunar Gateway itself will start. China is also planning to send the next Changelander to the surface, and those are only few examples. Whatever the mission will be flying there, it will definitely need some system of determining the orientation of the spacecraft. So usually traditional sensors are used in this purpose. They give us the information with respect to the stars, to sun or horizon. On Earth orbit, we also use magnetometers, but because of the very weak magnetic field around the Moon, we can't do that in there. So there is, however, an alternative which could support other sensors, and that is using the lunar surface itself as a source of information of what we are looking at. We could use a visual camera for this purpose. So what could we use as landmarks on the Moon? The area is split is similar all over the place with just a few different types as Mars and highlands. However, we have a huge number of craters visible on the surface that we could use as landmarks if we're able to tell what crater we have captured on the photo. About 1.3 million of craters have been identified in 2018. However, only 9,000 has been given an official name by EAU up to this day. We have a few types of craters on the lunar surface. The easiest to distinguish are the ALC and BAO types. They are similar. They are simple and small craters, bowl shape. They usually look very similar to each other. And thanks to that, it's not difficult both for human and for machine to recognize them. The only difference between those two types is the shape of their floor, because the biotype has a little bit of the flat surface up at the bottom, and ALC doesn't have any flat surface in here at all. So we can assume that we have an image taken from orbit. First step would be then to detect the simple craters on the photo and then try to identify them. In case you don't know how this object detection works, what you need is most importantly pre-trained model with some environment and a training set with labels. Then you fine-tune the model that you have with new data, and then at the end you get the new object detection model, and you can use it to detect whatever you want. For example, the trees on the satellite images, the cars, animals, basically whatever type of objects you can mark on images, you can train the model to detect it later. So as a training set, I've used around 300 images taken from a quick map tool with moon mosaic made of lunar reconnaissance orbiter photos. And on each of them, I marked all the simple craters. And in summary, it was more than 1,000 objects marked. And they were all marked as a single class, just a simple craters. The models that I used come from TensorFlow 2 library. I've decided to test two basic models, the efficient depth D0 and ResNet 50. The whole training process was run in Google Colab with 16 gigabytes GPU. Sorry, the next slide is, there's a lot of images, so it loads a little bit longer. I've tested the performance of this model on different lunar regions like Mars, Highlands, Poles. I've also decided to test it on direct images from narrow angle camera from LRO satellite, and also out of curiosity, I decided also to check the performance or Mars images. And I compared it with PyCDA. PyCDA is a free Python package for detecting the craters trained on the Mars images. At the end, it turned out that the precision of efficient DET and ResNet models was pretty similar. However, in case of recall, efficient DET was way better because it was just detecting more craters. So I decided to use this model for next phase. Also, what you can see in here is the fact that PyCDA performance was overall much weaker than both trained models. However, it was great in case of Mars images, so it proves that it was trained on this kind of data. And the last step in detection was converting the rectangular boxes, which you could see on the previous slides, to circles. So we could determine the diameter of the craters later. Okay, so now we have a crater detection model. Whenever we have a simple crater on the photo, we can detect it. However, we still don't know what crater are we exactly looking at. So let's move to identification now. And to even start discussion about crater identification, we need a database of craters. And in my case, I've created my own set, taking around 9,000 named craters from EAU, adding some of the Robbins database and some of my own. At the end, I had about 10,000 craters in my database. And then I've created the distance matrix, which shows the distance in kilometers between all possible pairs of craters. And it's saving this distance if it's below 300 kilometers. So the first step in identification process will be to measure the diameters of detected craters. And we can do that. But of course, we make here an assumption that we know how many meters each pixel in image represents. This value usually depends on camera used and the satellite altitude above the surface. After that, we choose our starting crater marked here in blue. Then we measure distance between starting crater and two randomly chosen craters out of the rest available on the image. We create this kind of triangle with distances. And then we measure distance from all of the other detected craters in the image. Now we know most of the distances between the craters, pairs on the image. And you can think of it as a graph where the diameter is node and distance is line connecting those nodes. By measuring the distance, we have identified in our matrix some of the craters sets that could be potential fit, as our calculations obviously have some errors because of the GSD parameter and other possible mistakes in the calculations of the distances. We need to find the set of the craters which has the most similar distances to those calculated from the image. So we then check what is the difference between distances in the image and distances from the database. We pick the set with the lowest difference. So in here, for example, you can see that the difference between the finally chosen set of craters and the original was 62 kilometers. And at the end, we are able to choose the set and tell what craters are on the image. Also, in some cases, if all the craters are between -30 and +30 degrees latitude, we are even able to calculate the coordinates of the image center. Similarly, through crater detection, I've tested the identification on multiple different images coming from different lunar landscape. In here, you can, for example, see images from highlands, mares, and poles, from raw image through detection and distances calculation to identification itself at the end, in the last row. The performance of identification turned out to be really good in mares and highlands especially. It was also good on the random image set. However, it turned out to be a little bit disappointing in case of poles, where the lighting conditions are obviously worse. And because of that, I decided to test the performance of detection and identification also on 3D models of lunar surface. For this purpose, I've prepared 3 different models, 15 by 15 centimeters each, representing different parts of lunar surface with simple impact craters. I've used a tool called NASA Moontrek to generate those models from DIM files. And I've been using a special laboratory setup to change the lighting conditions for each of the 3D models. I wanted to see how the performance of the identification will change. I've been rotating the model from 70 to 30 degrees. And for each of those angles, I've been checking identification results. Model A turned out to be easiest to identify craters together with Model B. They both had a high number of craters available on the surface. So in case one of them was not detected, the identification still had a high chance of being successful. However, the Model C did not have so many craters, so at the end, only 2 of 5 cases were identified correctly in the last model. Of course, there are some challenges that needs to be addressed. For example, the detection is not always correct, and sometimes it treats some other objects as craters, as the pit, as you can see in here. Also, hue transform gives sometimes wrong results. The biggest improvement, however, that I plan to do in the future would be to introduce detection of craters at different angles when the satellite camera is not directed to nadir position exactly. So in this project, I've created a prototype of a tool for identifying the craters. Here's like the quick simulation, visualization of how it works. Of course, there's a lot of work ahead to even think about using this in the future in practice, but I believe that it will be possible someday maybe to use such kind of system in the space missions. Such a tool would be also very helpful also for people working on lunar surface mapping, for example, not just in the orientation determination itself. There's a lot of work still to be done in this area. And that's all, I think. Thank you.